this notebook entry, you need your notebook, the real numbers page, a ruler, glue, and scissors. Cut out the 3 components on the solid or dotted lines. When you are done cutting, you will have 3 rectangle pieces as shown. Open your notebook to the next blank page. The title of this entry is Rational versus Irrational. Label the entry with the standard 7 NS3. This is a 7th grade standard, the 3rd standard in the number system category. The learning goal is, I can identify, compare, order, and plot rational and irrational numbers. Take your ruler and make a line 12 spaces up from the top. Trace from the pink line through to across the end of the page as shown. Trace a black line on top of the pink line on the left side of the paper. Trace a black line on the top of the pink line on the right side as well. Count down 2 spaces and trace a black line about 3/4 of the way across, coming from the left as shown. Then trace a vertical line down the page from this point. Count down 2 more lines and repeat this process. Count down 2 lines again and then repeat the process one last time. In the smallest inside box, label this natural. Natural numbers are the counting numbers starting with 1. For example, 1, 2, 3, 4, 5, 6, and so on. It does not include fractions or negative numbers or anything like that. It doesn't even include the number 0. On the next box, label this whole. Whole numbers include all the natural numbers plus the number 0. Do you see how the natural numbers box is inside the whole numbers box? On the next box, label this integers. Integers include all natural numbers, all whole numbers, and all of their opposites. So all negative numbers as well, but still no fractions or decimals. On the next box, the largest box, label this rational. Rational numbers include natural numbers, whole numbers, integers, including decimals and fractions. In the tall rectangle on the right side, label this box irrational. Irrational numbers don't include any of the others, and that's why it's boxed off over there on its own. Irrational numbers are any numbers that do not repeat, yet they go on forever. Some common examples include pi, which is 3.14159, and then it keeps continuing forever with no repetition. Other examples include the imperfect square roots. An example is the square root of 2. Count 5 lines up from the box we just made. Write common irrational number approximations. Irrational numbers go on forever with no end, and they do not have any pattern or repetition, so in order to use them, we have to just round them or use their about answer, which is an approximation. Here are some common approximations. Pi is 3.14 as a decimal, or 22/7 as a fraction. The square root of 2 is approximately 1.414. The square root of 3 is approximately 1.732. The square root of 5 is approximately 2.236. The square root of 6 is approximately 2.449. The square root of 7 is approximately 2.6458. Notice how I'm not writing the equal sign with straight lines. You make wavy lines to indicate that this is not exactly the value of these numbers. It is only an approximation or an about answer. We're going to take this component with all the lines on it and fold along the top edge. This will create a horizontal flap along the top edge. We'll put glue on the flap we just made and glue this 3 spaces below the learning goal. This allows us to still see our real number system notes below and leave some space on top for us to glue on the next component. Rational and irrational numbers make up the real number system. Rational numbers are repeating and terminating decimals. Any rational number can be written as a fraction. Remember that repeating and terminating decimals can both be written as fractions. Rational numbers include integers, whole numbers, and natural numbers as well. Irrational numbers are non-repeating, non-terminating decimals. This means decimals that don't have an apparent pattern and they go on seemingly forever without end. Flipping to the next component. Label on the top line should be real numbers, as all numbers that we list are going to be real numbers. Then on the left side label, we'll put rational numbers, and on the right side label, we'll put irrational numbers. We're going to take our real number bank component and sort all of these numbers as either rational or irrational, and there are some tricky ones in there. Okay, 2 pi. 2 with pi right next to it like that means that it's being multiplied by 2. It's 2 times pi. Pi is an irrational number. If you multiply it by 2, it does not change that, it just makes it twice as big as what it is. 102 is a natural number, so that's rational. Pi over pi is trying to trick us. Any number divided by itself is 1. 2 over 2 is 1. 10 over 10 is 1. 2.7 over 2.7 is 1. 0.3 divided by 0.3 is 1. So pi over pi is 1 as well. And 1 is a natural number, so that's rational. 4.567 is a terminating decimal. It has an end. That is a rational number. The square root of 2 is not a perfect square, so it is an irrational number. The square root of 50, I'll have to check my chart, so going back a few pages where we made that chart of perfect squares, 50 isn't on there, so this is not a perfect square, it's an irrational number. The square root of 49, so going back to my chart again, it is there. 7 times 7 is 49, so that's a perfect square. The square root of 49 is 7. That's a natural number, so it's a rational number. 0.3 repeating. Repeating decimals are rational numbers. Repeating decimals can always be written as fractions. If you remember, 0.3 repeating is actually 1/3. Negative 12 is an integer. That's a rational number. 0.5 is a terminating decimal, and it can be written as a half. That's a rational number. 4.7821 ... You see those 3 dots? That's called an ellipsis. It means that this keeps going on indefinitely. We do not see any repetition, and that ellipsis means that it's going on forever, so that's an irrational number. 1/2 is a fraction. It's a rational number. 6 cubed is 6 times 6 times 6. That's 216, which is a natural number, so it's rational. Negative 9 3/4, that's a fraction. It doesn't matter that it's negative. It's a rational number. 9 with negative 2 exponent. Anytime you have a negative exponent, you just drop the 9 squared into the bottom of a fraction. We put 1 on top. Now the negative is gone. 9 times 9 is 81. It's 1 over 81. That's just a fraction, which is a rational number. Disclaimer, you don't need to memorize or understand negative exponents. That's something you'll learn in Algebra 1. Pi over 2. Again, this is trying to trick us. Yes, that's a fraction, but pi is an irrational number, and dividing it by 2, which is what this is doing, does not change that pi goes on forever with no repetition. 2 times the square root of 5. When a number is right up against a square root like that, it means you're multiplying them. The square root of 5 is not a perfect square, so multiplying it by 2 doesn't change it. It's irrational. Come up with 3 additional examples for rational and 3 additional examples for irrational numbers. That's 3 of each, so 6 more numbers. Try to come up with something crazy or unique. So what we've just done is identify whether a number is rational or irrational. We still need to be able to compare, order, and plot them. Turn to the next blank page. Label the top as compare, then order is in the middle, and plan is near the bottom. Place them as shown. Write the following as examples to compare. 0.4 and 2/5 with a line in between. Pi and 3.14 with a line in between. 0.33 and 1/3 with a line in between. and -7/8 and -0.8 with a line in between. To the first example, I'm going to convert 2/5 into a decimal in order to compare them both as decimals. I'll do top divided by bottom. 2 divided by 5, which turns out to be 4/10 or 0.4, that's the same as the decimal 0.4, so they're the same. I'll write the equal sign between them. Next example, I need to convert 1/3 to a decimal, and I know that this is 0.3333 repeating. The other decimal is just 0.33, and it stops, it terminates. Remember, I can add zeros to the end of terminated decimals, and it will still have the same value. So 0.33 has the same value as 0.3300, and so on. So 1/3 is actually greater than 0.33 because it continues with the value of 3, and 0.33 just ends. Pi is 3.14159, and then it just keeps continuing forever, and I don't have that memorized because it's infinitely long. 3.14 is just a decimal number. It stops at 4, but 3.14159 pi keeps going. Pi is larger than just 3.14. Last example, I'm going to divide 7 by 8 to convert this to a decimal. The decimal is 0.875, but remember it's negative, so it's negative 0.875. The other number is negative 0.8, so negative 0.8 is greater because negative 0.875 is more negative than negative 0.8. It would actually be to the left of negative 0.8 on the number line. A quick side example, if we compare -3 to -4, -3 is actually the greater number. Even though 4 is bigger than 3, the negatives change this. Would you rather owe $3 or owe $4? Owing $4 is worse, so it's technically a smaller amount of money that you have. Owing $3 is slightly better, so it's the greater amount. Okay, let's order a set of numbers from least to greatest. 0.2, -1/10, and 14%. Let's make them all decimals so we can compare them easily. 0.2 is already a decimal. -1/10 will be -0.1, and 14% will be 0.14 or 0.14. So the least will be the negative number, -1/10. It's like bad to be in negatives. It's going to be the smallest number. I will write it as it originally was. Then 14%, then 0.2. 0.2 being the largest. Try another set on your own. Order the following numbers from least to greatest. -1/4, -0.21, and -20%. When you finish, check your answer with a partner. Use your ruler to make a straight line in the plot section. Put an arrow on both ends to show that numbers can go on forever, both positively and negatively. Mark the middle as 0. I use the ruler's centimeter side to make equal spaces going up and down, and then label them counting up and down. It goes from -6 to +6, evenly spaced 1 centimeter apart each. We're going to make a bank of numbers on top. A is pi, B is the square root of 2, C is the square root of 16, D is 2 times the square root of 9, E is -0.5, F is the negative square root of 25, and G is -4 3/4. I'll do a couple to get you started. Okay, A. Pi is approximately 3.14, so I'm going to make a mark, a dot, slightly more than 3. And I'm going to label that A. All right, E, which is -0.5, it's going to be exactly halfway between 0 and -1. I'll put a dot there and label it E. Try the rest out on your own and then check your answers with a partner. Don't forget to go to the table of contents and write in this notebook entry with corresponding page numbers.